Howdy everybody. In this video we are studying electric capacitors and their application to electric circuits. So this right here is a capacitor. This is one of our really giant demonstration capacitors, which has a capacitance of 1 farad, which is really big. And so this would not be practical for most applications. Another example capacitor that I have right here is this guy. This is still pretty big for a capacitor. You'll notice that both of them have like a cylinder shape. And so in any electrical device, if you see some cylinder-shaped components, chances are those are capacitors. For instance, if you pry open a calculator, you'll notice a lot of these shaped things inside of it. So before we get into a capacitor in a circuit, I don't want to take for granted that you know what a switch is and what it does and how it affects the voltage in a circuit. And so I'm going to set this aside for 1 second and demonstrate the switch. And I've got a switch connected to a light bulb in series, and then these two alligator clips are going to my battery emulator, which is right over there. And so when I switch this thing on, so you'll notice that the red light is on and it's set to the 3-volt setting. You'll notice that even though the switch is on, that the light bulb doesn't light up. If I close this switch, let's turn it like that, close it like that, now you notice that the light bulb light up. So there wasn't a complete conductive path until I closed this switch, and all that a switch is a basically movable conductive path. Air in between these two things, now conductor in between those two things. If I were to take a voltmeter, so I got a voltmeter right here, and do some measurements of this circuit, the voltage across the light bulb is like 2.7, almost 3 volts like the battery was. If I measure the voltage across the switch, let's kind of do it here and here, notice that it's practically 0, not exactly 0 because the switch does have a little bit of resistance, but very close to 0. By comparison, if I do across just this wire right here, I get very close to 0, but not exactly 0. So all these components have a little bit of resistance. Now, if I undo the switch, if I open it, notice that the light bulb goes out. And if you were to predict the voltage across the light bulb, hopefully you're going to tell me it's 0. And it is 0. If I measure the voltage across the switch, remember that the loop rule still has to be obeyed. And the battery emulator is still on. And so going from the battery back to the battery, I have to have a net voltage change of 0. So 3 volts are being gained going through the battery. Approximately 3 volts have to be lost here. And they're going to be lost over the switch. Notice that when I put the voltmeter on, I get about 3.2 volts. So if a charge were to move from this side of the switch to this side, everything else in between the battery as a conductor, that's where it's going to lose all 3 volts of energy that it gains from the battery. And so the voltage across my switch in this situation is basically equal to the voltage across the battery. So that's kind of an important thing to realize when we introduce a capacitor. I'm going to undo this wire right here, and I'm going to leave this switch in the circuit so that you guys can clearly see when the circuit is closed versus when it's open. So I'm going to leave the battery emulator on the entire time today. So let's introduce our capacitor. Here is our capacitor. This is brand new out of the box. These things are a little tight. There it goes. Like literally, I just opened the box to get this one out moments ago. Okay, there we go. So now our capacitor is in series with my switch and my light bulb. So this is just one loop right here. If I were to measure the voltage across my switch again, I still get 3. If I measure the voltage across my capacitor, I get 0. If I measure the voltage across the light bulb, I get 0 as well. So the first thing I'm going to do is just close this switch. I'm not going to worry about measuring anything right now, and observe what happens to the light bulb. So 3, 2, 1, close. And what you should have noticed is the light bulb was initially very bright, just like it was before, and then it slowly got dimmer over time, and now that light bulb is so dim that it is practically not glowing. We could say that the light bulb is not glowing at this point. And so what happened? Like, the battery is still on. I didn't reach over here and turn the battery off. The switch is still closed, but now the voltage across the light bulb looks to be 0, and it looks like there's no current going through the light bulb. If I reintroduce my voltmeter and take some voltage measurements again, putting this across the light bulb, I get very close to 0, 0.02. Putting it across the switch, I get very close to 0. So where are my volts? I still have to have a net drop of 3 volts going around this loop. So if I put it on the capacitor, notice that I get a voltage drop across the capacitor of about 3 volts, which is exactly what the battery voltage was before. And so the charge on this capacitor, now it's charged, is causing it to have a potential difference. This capacitor is now fully charged, and so on the positive, which would be this side, end of the capacitor, I've got a bunch of positive charges. On the negative side, I got a bunch of negative charges, and so there's a potential difference between the sides of the capacitor. So how can I demonstrate that there is a potential difference across the capacitor? First thing I'm going to do is I'm going to undo this switch. And if we just measure the voltage, you'll notice that it dropped just a touch, but not a whole lot. So now the battery is not in play at all. The only voltage is due to that capacitor. You may notice that it's kind of sort of dropping just a little bit. Let's make it drop a little bit quicker. Let's take another light bulb. And basically what we're going to do is we're going to make a new loop connecting the 2 sides of the capacitor. So I'm going to connect one side of my light bulb on this side, the other over here. Watch carefully as I do that. And you'll notice that the light bulb turned on and that it gradually got dimmer. So basically what I did was I discharged the capacitor by creating a complete loop that goes from the positive end of the capacitor through the new light bulb and then back to the negative end of the capacitor. So now if I were to measure the potential across my capacitor, I'm back to essentially 0. If I measure the voltage across this light bulb, well, it's not part of any kind of circuit, so it's 0, and then my switch should be about 3 again, like it was before. So let's run that back again. This time I'm going to clip the voltmeter in with the capacitor so that we can see in real time how the voltage changes. Okay, so now this voltmeter is telling me the voltage across my capacitor, and it's reading just a little bit more than 0. There may still be some charge on the capacitor, and I can get rid of that extra charge by kind of short-circuiting. So I'm just going to connect like a wire across there, and then you notice when I did that the voltage dropped to 0. And so the light bulb has significant resistance, so maybe not all the charge left the capacitor, but most of it did. I can get rid of the rest of it just by short-circuiting the capacitor like this. If it wasn't connected in that circuit, I could also just touch the 2 cables running out of there together. Okay, so this is measuring the voltage on the capacitor. I'm going to go ahead and close the switch, and we're going to observe how that voltage changes as the capacitor charges. So notice how as the light bulb got dimmer, indicating its voltage dropped, the voltage across the capacitor went up as this voltage went down. If I leave that there, let me go ahead and open up the switch again just so y'all know there's no tricks, and then connect my other light bulb to my capacitor, we can see in real time then how the voltage drops. As all the charge is moving in the reverse direction, going through the light bulb, and then that's being dissipated as heat and thermal energy in the light bulb. And we'll get pretty close to 0. can go ahead and do this just to make sure. Okay. So let's do one more demonstration of this. This time I'm also going to connect a voltmeter to this light bulb. And I'm going to move this one over here since the capacitor is on the left. Bring in a second meter like this. So there's the prongs to the second meter. So right now nothing's happening there because there's no charges involved. The voltmeter on the left is measuring the voltage across my capacitor, whereas the voltmeter on the right is going to measure the voltage across my light bulb. And we can check to see how that's working if we just leave the capacitor bypassed by this wire here. If I close the switch rather, notice that my voltage jumped up. Let's see if I can prop this up and get rid of this glare. Let's see if that'll be enough. Okay. Alrighty, so let's open up the switch. Let's get this wire out. And then we're going to closely watch these voltmeters rather, and see how this one, which measures the voltage of the capacitor, changes in response to this one, which measures the voltage of the light bulb. Here we go. 3, 2, 1, ignition. So we notice as this one's going down and starting to level out here, that this one goes up. And if we were to play that back, hopefully we would notice that they always add up to give us about 3 volts, because the loop rule still has to be obeyed. So the voltage across the switch, which is 0 right now, plus the voltage across the capacitor, plus the voltage across the light bulb always has to add up to 0 when we add the voltage of the battery. So battery minus switch minus capacitor minus light bulb has to add up to 0. Next, we're going to look at how the current is affected by a capacitor. And again, I'm going to start with a circuit that does not include the capacitor. My battery is still on. I haven't switched it off this entire time. And then the wire that was over here, I've removed and replaced with my multimeter, this time set up as an ammeter. And so this is still in series with everything else. Current has to go through the yellow wire, into my meter, through the black wire, and then through the switch, this wire, the light bulb, which is our little tattletale, this wire back to the battery. And so initially my switch is open. You'll notice that there is 0 current and the light bulb is off, as you would expect if the switch is open. If I close the switch, your light bulb came on, and notice now that there is a relatively steady current of about 0.33 amperes. So in a circuit, an open switch does not allow any current to flow through it, whereas a closed switch allows a lot of current to flow through it. If I measure the voltage across this, that would be 0, meaning basically it's offering no resistance to the circuit, and we get a very bright light bulb as a result. So the next thing we're going to do is replace this wire right here again with the capacitor. Just like that, just like that. And we're going to measure the current as it changes as current flows through the capacitor. So just like with the voltage, the current is going to be rapidly changing. So when I connected the switch with the voltmeters, we saw the voltage was changing over time. We're going to see the same thing for current. So the first number that flashes on the screen, hopefully, is about the same as what the current was before, about 3 amperes, give or take. So watch that number carefully as we close the switch. 3, 2, 1, ignite. So notice that we again started off with a relatively high current, and it's pretty much the same values we had before, of about 3.33 amperes. And then as the capacitor charges and the voltage across it increases, the current through the capacitor decreases. Basically what's happening is you consider this to be a battery in reverse. Imagine if I replaced this capacitor with a battery that was turned in the opposite direction as the battery emulator, like the yellow and blue alligator clips. Basically what that would do is cause a reverse potential difference that would negate, if you will, the potential difference from the battery. And so that's what's happening here. This capacitor is fully charged and it's got a voltage of about 3 volts across it, just like we had before. If there is 3 volts here and there's 3 volts in the opposite direction coming from here, basically that means that no more charge is going to be able to move through the circuit. So the last thing I'm going to show you here is the current when we discharge the capacitor. And so I've replaced the ammeter back with a wire, and I moved the ammeter over here. And so I'm not going to see any current just yet, because I'm not going to measure any current until I connect this wire to the second light bulb to discharge the capacitor. So I'm going to go ahead and close the switch, and I'm going to let my original light bulb tell me when the capacitor is fully charged. So this isn't reading any current because this light bulb isn't connected to anything right now. So this light bulb is now out. My capacitor is pretty reasonably charged. I'm going to go ahead and open the switch so the battery's not in play anymore, and then connect the capacitor to my second light bulb, and let's watch the current. So you'll notice it started off pretty high and is gradually going down as the capacitor discharges through this light bulb. Now this light bulb is pretty much out as well, and this is going to drop off to 0. So as charges move from one end of the capacitor to the other, there's only a finite amount of them, and so there's not infinite charge stored in the capacitor. There's a very specific amount given by Q equals C delta V. And so as that charge runs out and this voltage drops, so does the amount of current it can supply to the exterior or rest of the circuit. And so kind of your takeaways from this: number one, Kirchhoff's rules must still be obeyed. And so if this is charged to 3 volts, that's got to be included in any loop rule calculations. Second thing, for the purposes of generating current, move all this stuff out of the way, an uncharged capacitor is basically like a closed switch. When the switch is initially closed, we had a very high current. When the capacitor is uncharged, we get a very high current. A charged capacitor is basically like an open switch. When the switch was open, there was no current going through it, just like there is now when the capacitor is fully charged. And so a charged capacitor, you can think of being like an open switch, like it offers a lot of resistance to your circuit. A uncharged capacitor basically acts like a closed switch, where it offers almost 0 resistance to your circuit. If you can kind of understand those two key ideas, then we can start understanding how circuits are affected by a capacitor. And so we've got a lot more examples to come down the road. We're going to start connecting these in series and parallel, and what happens when we have another branch to our circuit and things like that. But for now, that's kind of the key idea we want moving forward.